Hey Brian, so this is my indoor garden. It started out as just me buying an item from the dollar store that said that you could just add some water and some dill will start growing. And I added a little water, then probably too much, then I forgot to water it. But at any rate, the dill started growing. So then that got me on this whole campaign of planting seeds and seeing what grows. And it turns out a lot of things do. And so as we're exploring, we always want to follow our heart, being that only love ultimately exists, and also recognizing that, as somebody recently said, nature is always right. So instead of having to reinvent things from scratch, let's just look at the answers from nature. And one thing that always stood out to me is that there are no commodities, that if you plant cucumber seeds, for instance, every seed is different, and there is no generic cucumber plant, just like there's no generic person who goes through customs saying, I'm a person, let me in. I mean, everybody has their own story, their own uniqueness, and based upon lots of different factors, the genes within the seed, the soil content, the sunlight, the water content, all the minerals within the soil, the microbiology surrounding these things, the airflow around them, based upon countless factors, each plant has its own story, and they are each perfectly precise in their own story and also perfectly imprecise relative to theory. So when we're talking about geometry, the idea is not to get exact geometric answers because exactness is innately commoditized. The idea is to use math within its context in combination with intuition to point us in the right direction, but ultimately to follow nature in terms of how the answers have been configured, and as inspiration for how future answers may emerge. So we always want to keep that in mind, that with nature there's uniqueness, and looking at the Sasquatch, at least within our customary ways of perception, their structures are quite coarse, and so we don't necessarily need a lot of high precision in creating sacred geometries, just enough to accommodate the circumstances. Okay, so with that as a lead-in, let's talk about the geometry. Hey Brian, so I told you I would walk through my studies of geometry, and they began with this book, Pyramid Power, which talks about special phenomena that are reported to have happened with pyramids, where things don't decay, like milk doesn't spoil when it's reportedly under a pyramid, and razor blades reportedly become sharper under a pyramid. Now, I can't vouch for these things, but it's one of these books that provides a lot of information that, if it's at least partially true, it's like it's worth its weight in gold. So it's a very valuable book, but I haven't had time to really dig into it too much until lately. And so one of the passages in the book talks about how a cone can have the same effect as a pyramid. Now, in my opinion, a cone is better because you don't have to worry about the orientation. It's the same as if it's from any direction. So I figured I would make a cone, and I also want to follow my heart and be sensitive to nature. So I had a trash can lid, and I created a circular base with the trash can lid, and then I figured I need to know what the height should be, and nature has the golden ratio, and so I figured I'd make the height to the radius the golden ratio, and the angle involved in doing that is the exact same angle that's involved in taking a dodecahedron and putting pentagonal pyramids at the top of it for a small stellated dodecahedron. So this is the top of one of those small stellated dodecahedrons, and so the dodecahedron would be defined by these valleys. So we have the top pentagon of the dodecahedron, and then the beginning of another pentagon here, another pentagon, another pentagon. And I didn't include the bottom half, for simplicity here. But if we build a pyramid atop each of the pentagons, and we angle them so that the faces are coplanar, then the angle between one of these vertices and the centroid, which I stumbled upon on the internet, no coincidences, that the angle involved in the corner to the center here, that's the same angle as with the golden ratio in the cone here. It's the exact same shape. I mean, this fits exactly in the top there. So that's what got me started, and then I was focused upon the dodecahedron and the other platonic solids. So let me break the video and show you what I've got there. Okay, so there are 5 platonic solids, and I was originally going to make them using rods that would create a frame, but it turns out that you can create them even in an easier way by stacking spheres. So we have the 5 platonic solids here. We have the tetrahedron, where you take 3 spheres, put them all in contact with one another, and then fit one on top, so that no matter how you look at this from any angle, it's the same tetrahedron shape. Okay, and then the next one is the octahedron. So you take 4, put them side by side, and put one on the top and one on the bottom. And again, no matter what angle you look at this, you can rotate it around. You keep seeing the same type of shape, and you can rotate it up and down, and you keep seeing the same type of shape. There are always 4 in the background and 1 in the front. And if we look at it here, it's the same situation. 4 in the background, 1 in the front. 4 in the background, 1 in the front. 4 in the background, 1 in the front. Okay, and then the next shape, which is related to that, is the cube. Everybody knows the cube. You take 4, 4, 4. It's always a cube. Okay, but those two are related, and these last 2 are related as well. The outlier is the tetrahedron, and we'll get into the details of that a little bit later. But the next one is the icosahedron. So this is where you take 5 and put them in a pentagon shape. So you're getting them all as close to each other as you can. So you're creating a symmetrical, regular pentagon in the middle, and then putting 1 on top. Okay, so you have 6 there, and then you do the same thing over again. 5 behind, 1 on top, and then you stagger those 2 layers in the middle. So we have, let's say, 1 on top here, 1 on the bottom, and then we have our 5 around here, our 5 around here, and those 2 sets of 5 are staggered with one another. And so we could see this as a side view with the 2 layers of 5 staggered, like I was pointing to. We could also see this as a top view now with the 5 behind it, and then flip it over, and we have the 1 on top, the 5 behind it, and the 2 layers of 5 staggered. Again, same from any angle. And then there's the dodecahedron, the most difficult of these to make. So we start out the same way. We take 5 equally spaced, but instead of putting 1 in the middle, we just continue that pattern in 3-dimensional space. So we have the 5, we flip it over, we have the 5 on the bottom, so let's say this is the top. We flip it over, and we've got 5 on the bottom. So I'm holding it top and bottom here, and then each time we have 2, we use that as the side of a pentagon. So here on the top we have 2, that's the side of a pentagon. The bottom we have 2, side of a pentagon, and you can see those middle pentagons are staggered. So it's quite related to the other shape, and we'll talk about those relationships in the next one here. Okay, so we talked about the 5 platonic solids, and we mentioned that the tetrahedron is sort of its own. These 2 are related to each other, and these 2 are related to each other. Okay, so let's look at what we mean by that. So if we started out with the same tetrahedron, and we then put a different colored sphere in each of the valleys, so 1 on top, 1 on each of the 3 sides, 1 on and 1 on each of the 3 sides, we end up with exactly what we started with. The blue ones are now the outermost vertices of the tetrahedron. So we start with a tetrahedron and we fill in the valleys. Every time we have a valley of 3 pieces, naturally a sphere fits into that. So we do that everywhere we can, and we get the same shape again. That's the only one of the 5 Platonic solids for which it repeats like that. And we could, I expect we could do that, to infinity. So it's a repeating pattern. And we've got another couple models there. So we start with the silver ones, we put white ones in the valleys, and we end up back at the tetrahedron again. Start with the white ones, add silver ones, same situation. So that's the tetrahedron. So let's take care of the tetrahedron there. Okay, so now the octahedron, this one, and the cube are related similarly. So everybody's familiar with cubes. Let's start with that. So let's say we start with a silver cube in the middle, and we put white spheres in each of the valleys. When we do that, those white spheres now constitute an octahedron. Or we could do it the other way around. We start with an octahedron in white here, add silver spheres to the valleys, and we end up with a cube. So as we fill in the spheres, the tetrahedron always stays a tetrahedron. The octahedron oscillates to a cube, to an octahedron, to a cube, to an octahedron, and same thing with the cube, cube to octahedron, cube to octahedron. So these two keep oscillating with one another. Tetrahedron stays the same. And then these two also do an oscillation. So we could start, let's say, with a dodecahedron in silver. So we have the 5 on top. We have those, classic dodecahedron, staggered pentagons. Maybe a little bit hard to conceptualize seeing it as spheres, but those staggered pentagons, pentagon on the bottom. We fill in every time there's an obvious place for a sphere. So we have these, these big holes in the middle. So we land a sphere on top. The sphere sits a little bit above the hole size. We do that everywhere we can. And we end up having, instead of 5 on top, we have 1 on top. And instead of 5 on top, we have 1 on top. And instead of having pentagons on the side, we have staggered triangles on the side. So 1 on top, 1 on the bottom, and they lend themselves to these 10 triangles in between. So we start with the dodecahedron, we get an icosahedron, and if we start with an icosahedron and add silver spheres, we get a dodecahedron. So those two oscillate with each other the same way that the icosahedron and the cube oscillate with one another. So we can organize the Platonic solids into 3 categories here. We have the tetrahedron, which is its own animal, tetrahedron. We have the tetrahedron, icosahedron, and cube. And we have, octahedron and cube, and then icosahedron and dodecahedron. Okay, so what we're looking at here in yellow, let's begin with looking at what's in yellow in terms of the valleys. So let's not look at the pointy parts, let's look at the valleys. So we have a valley here, valley here. We have 5 valleys comprising a pentagon on top. So I'm pointing to the valleys there. And if you continue looking at the valleys, 5 alternating with 5, and 5 on the bottom. So if we look at just the valleys, what we have here is a dodecahedron. And then we created a pyramid, a pentagonal pyramid on each of those pentagonal faces. And the angle of that pyramid is such that if you look at any side, the five angles of the pyramids are coplanar. So if you look at this, it's like a star. It's all in the same plane. Each of those sides of the pyramids, and that's the same shape that we started out with. The golden ratio. The golden ratio being the distance from any of these vertices to the center of that pentagon, or that's the base, and then the height relative to that base, those proportions, height to base, height to base, are the golden ratio. Okay, so this shape made in paper, in yellow paper, is known as a small stellated dodecahedron, which is a jawbreaker of a name, and it looks to me like a very beautiful three-dimensional star, a beautiful three-dimensional Merkaba, and it seems like it wants to be called a harmony star, so that's what I call it. And then if we, just follow our intuition, okay, so what should we do next? Well, we've got these pointy parts, let's connect them all. And since everything is symmetrical, we know that when we connect them, we're going to get equilateral triangles. So we do that, and we get equilateral triangles all over the place. And if these are equilateral triangles, then that means that we are at a Platonic solid, because everything is the same shape, same size, same angles. And if we look at the wooden dowels, those are tracing out an icosahedron. So we went from a dodecahedron to an icosahedron. And then if we build out from those triangles with equilateral triangles, now I did this physically rather than computationally, but physically, if this was built out with equilateral triangles, in other words, tetrahedrons, and that just by inspection brings us back to the dodecahedron. So on top we have 1, 2, 3, 4, 5. You can imagine this being a face of a dodecahedron. Same thing here. We have 1, 2, 3, 4, 5 pointing downward pyramid. Here we have, another downward facing pyramid, and the exact opposite, the same thing on the bottom, just with the pyramids staggered. So we have the outline of a dodecahedron. So this is just illustrating in another way that oscillating relationship between the dodecahedron and the icosahedron. We started out in the valleys here with a dodecahedron. We then built pentagonal pyramids angled such that the angles are all in the same plane, which, no coincidence, also involves the golden ratio being the proportions of the height of the pyramid relative to the centroid to vertex dimension. We then used equilateral triangles to get to our icosahedron, and we used tetrahedrons to get to our dodecahedron. And I'm just thinking out loud here. If we're using exact tetrahedrons to get from our icosahedron to our dodecahedron, if we're using exact tetrahedrons to get from the icosahedron to the outer dodecahedron, I'm thinking in theory that that has to work out, because we're starting with a Platonic solid. We're using Platonic solids symmetrically. We have to end up with another Platonic solid. So we don't really need to do any math. I mean, physically it appears that way, and logically it does as well. So that's the relationship between those two. Now, as I mentioned in the previous video, this harmony star, this shape in the middle, is very intriguing to me. So you can conceptualize it as two three-dimensional pentagonal pyramid chevrons superimposed upon one another. So in this case, we've shaded this particular pyramid. Okay, so Brian, in the previous video, sorry my phone died, but I think I was talking about the pyramid shape in the middle, the one that has the chevron because of the truncation at the bottom. So if we take one of these pyramids and we color it, so let's say we color it blue here, sort of blue-green, and then we color the other faces in the same plane. So in this case, we have the triangle here and the other two faces there. And we can see that that's like a pyramid facing upward, and the same thing on each side. And if we paint the opposing one in, or color the opposing one in orange, you can see how those interweave with one another. So it looks like a three-dimensional version of a 2D, of what's, you know, conceptualized in 2D as a Merkaba. And so we have that, oops, I think I just broke something. So we have that, that chevron, that pentagonal chevron, and then the same thing, the pentagonal chevron on the other side. And for each case, we have sort of a hat, a halo around it, there and here. And then the remaining faces are, the ones that are not colored are sort of these window-like facades between the two, window-like facets. So that's that shape. Okay, so this is one of the pentagonal pyramids, as we saw on the Harmony star over there. And we can create this by just taking a semicircle, 180 degrees, dividing it evenly in 5, and then creating triangles, folding those triangles together, and we get this. Now, instead of a semicircle, if we use okay, let's stay with the semicircle. We use a little bit of geometry and trim out the bottoms, and we end up with the shape that we were looking at inside of the Harmony star over there, the pentagonal chevron shape. And then if we go back to this, and instead of using a semicircle, if we use a full circle, then we have more material to work with. And looking at this, these middles seem to want to fold to the inside. So we have outside folds. The middles seem to want to fold to the inside, but if we do that, we run out of material. So instead of starting with a semicircle, if we start with a full circle, same shape, we get this. And we can do exactly that. We can take each of these, facets, and we can fold the middle. And okay, that's a little bit better. So we take the facet, we fold the middle inward. And as you can see, this is parametric. So as we press it down, the height reduces and the piece widens and it actually flips over. So I started with this shape where we're folding to the inside, which seems natural, but actually you can go all the way and invert this the other way. So just to show you that, this can be any height, even a negative height, and everything will accommodate what it does. So some of the interesting shapes involved in that Harmony star. Okay, now getting back to those pairs of platonic solids that interconnect with one another, it raises a very interesting question. If we have a dodecahedron, and an icosahedron, and they are very much related to one another, that they keep oscillating as we fit spheres into the valleys, then it raises the question, well, what would it look like if we superimposed those? In other words, if we conceptualized each platonic solid as a sphere with certain vertices that are all equidistant from the center, what does it look like if we superimpose these two shapes in that manner? And the answer has been in front of us all along. The answer is in the shape of a soccer ball. So we have, let's say, a pentagon and 5 other pentagons. It's kind of hard to see because this one's not colored the way a soccer ball traditionally is, but we have center pentagon, 5 surrounding pentagons, and you've got hexagons in between, and those hexagons are arranged pentagonally. So it's a shape that for which each of the centroids of the pentagons and the hexagons represents one of the vertices of this theoretically combined icosahedron, dodecahedron shape. So if we connected the centroids, we could get something that has triangles that covers its surface, but I would trust that somebody's already done that and established that those are not equilateral triangles, and or that they're not at the same angles relative to one another, and therefore the result is not a Platonic solid. But there are other things we can do. Let me show you those. So we could start with a dodecahedron, which we have in green paper here, dodecahedron in green. And then we could go from the vertices some distance upward and create pentagonal pyramids like we did before, but this time not aiming for the golden ratio and not aiming for all of these to be in the same plane, just going up some, let's call it some height for now. And then what we could end up with is a situation where these triangles, these equilateral triangles, combine to form diamonds. And so the entire surface is covered by diamonds, a diamond here, a diamond here, diamond here, and the whole surface is covered with these diamonds, these parallelograms. And it seems pretty close to a Platonic solid, except that because these are parallelograms, the angles are not the same. This is an acute angle, that's an obtuse angle. So that being the case, it's not a regular polygon, so therefore it's not a Platonic solid, but it is the same diamond shape, the same in-plane diamond shape, repeated, covering the entire surface area with the same angle sets, the connection of five, diamonds, and the connection of 3 diamonds, staggered across the surface of the shape. So one way we could approach this synthesis of the icosahedron and the dodecahedron is to try to put all the vertices of both shapes on a sphere, which is what the soccer ball would show. Another is to create to facet the resulting shape with repeating diamonds over the full surface area, and that's what this is. And then, of course, the other question is, well, can you do the same exercise with the relationship between the octahedron and the cube? And the answer is yes. So you can take a cube, you can build pyramids from its corners, and you end up with what's shown in red here, which is a diamond-covered shape that represents the synthesis of the vertices of the cube, which we're seeing as the corners of the cube in orange, and the vertices of an octahedron, which we're seeing as the tips of the blue members. And we're synthesizing that and tiling its surface with these red diamonds, each diamond being flat and in its plane. Okay, now we talked about sacred geometry. Now I'm getting now into what I call intuitive conjectures. This is just sort of speculation on my part, but I think it's speculation worth considering, which is what I'm doing. The idea that there's metaphysical power within a cone seems to relate to consciousness being omniprevalent and to art. So if we have a cone, as a little child, my first inclination would be, well, what's it look like on the inside of the cone? Theoretically, could I go down the drain and experience that? So there seems to be an intuitive consciousness that follows the inclinations of art. And if that's the case, you can imagine, let's say, lots of little orbs that are generally unseen to us that are traveling down the cone, bumping into each other. And so there's this order that's facilitated. The conical shape is intriguing. It's developing an order. It's causing engagements between these beings, and it's causing harmony. It's resisting disorder. It's resisting entropy. And the definition of life, arguably, is entropy resistance. In other words, life is a duration for which we resist disorder. So instead of Instead of a room becoming messier, for instance, life would make the room cleaner. Life is a process of entropy resistance, and sacred geometry and art in general, for that matter, seems to have the same effect. It's a situation where it causes people to stop, to reflect, to recognize commonalities in other admirers of the art, and to inspire artistic creations of their own. And so, again, it's speculation, but I'm speculating that geometries, just the geometry itself, has that effect as spirit beings travel through the geometry, and as they get to that apex, they're increasingly orderly, and then as they divert out from it, they're disorderly because they're going back into the ether. So this would explain why we have order inside of pyramids and disorder above them, why there's trouble flying over what I hear are the pyramids under the Bermuda Triangle, and reportedly the pyramids of Giza. So there seems to be a blend between art and science in how in how nature operates. So getting back to nature, you aren't going to see a cone this perfect in classical nature that we see, but we will see lots of cones in nature in the form of seashells, very elaborate seashells that have curves and, I guess you could say, imperfections, but you could also say character. And so if we're trying to create a cone and see what happens inside of it, probably makes more sense to start with a seashell, with a naturally existing cone itself, put something inside, and then see what happens. I haven't done it yet, but that seems like an obvious next step. And so just turning to nature, looking at these cones. This concept also, this concept of cones also seems to relate to the Lemurians reportedly living in Mount Shasta, to Shiva reportedly living within a mountain, to the Ponti reportedly living in a mountain. If these mountains can be conceptualized as conical pyramids, then their geometry lends themselves to metaphysical empowerment. So we're just following nature to see what happens.